In this video, we're gonna solve a system of linear equation using the Gauss reduction. So let's just take I don't know, x, something simple, something in the xy plane. So x minus 3y equal 3, and 3x minus 5y equal 3. So this is going to be our system of equation, which may make you laugh because, this is like pretty straightforward. So there is, no reason to do it with Gauss. But the reason why I want to show you with Gauss is that Gauss is actually very, very, very useful for higher dimension system of linear equation, because it's it's actually easier to compute, and it's actually easier to find solution for high systems. So this is actually pretty simple. Almost ashamed of doing it, but because it almost make you laugh. But let's just stick with something very simple in R2 to start with. So the matrix associated with this is going to be 1, negative 3, 3, 3, negative 5, 3. So the reason why I'm adding those lines is that I want to keep the values over after the equal separated. Because when I did the video about the rank of a system of linear equation, I show you that the rank of the complete matrix has to be the same of the rank of the incomplete matrix of the matrix of the coefficient, because otherwise the system is inconsistent. And I show you an example of when the system is actually inconsistent. So this is actually a good practice to keep them separate, keep what is what, you know. Okay, so once again we're gonna have a one, hopefully a one and a one here, and a bunch of zero. Well, not a bunch of zero, just a zero, because it's a pretty simple one. Is is an R2 one. So okay, well, 3 and 1 easy values. So let's do the second one. Minus, gonna have a 0 here, so minus 3 times the first. Okay, so the first is gonna stay the same. I have 3, and now we're gonna have 0, 4, negative 6. So 3 times 1, 3, 3 minus 3, 0, and the other, you get the calculation. Those are pretty easy. Okay, now I want to simplify it even further. Those are linearly dependent. I can divide all of them by 2, but I can do better. I can multiply I can divide all of them, both of them by 4. So, but I cannot divide, so I have to multiply. So multiply the second by 1/4. Okay, 1/4. Okay, so 1, negative 3, 3. It's gonna stay the same. 0, 1, and I'm already happy. 3/2. But can I do better than this? Well, not really, but I just, well, no, actually, yes, I can get rid of this 3 here. So I'm gonna multiply the second by negative 1. So by doing this, I'm gonna get seconded by -1, so it's going to be 1, -3. 3 is going to be the same, and then 0, -1, and 3 over 2. Okay, this is my new matrix. And now I want to have, I'm going to make, okay, I'm going to do the first one minus 3 times the second one. Why 3 times? Well, because I want to get rid of this. So that's 3 times the second one. So I'm gonna get rid of this. So 1, 3 times the second one. So 3 times 1 is gonna be -3. -3 minus 3, it's gonna be -3 plus 3, so it's gonna be 0. So this is gonna be 0. And this one is gonna be -3 over 2. And this one is gonna stay the same, -1, 3 over 2. And then I just bring this one back to positive. So multiply the second one by -1. So 1, 0, 3 over 2, 0, 1, -3 over 2. Okay, so I also found those two are the pivot. So the pivot H2 pivot equal 2, so the rank is 2, so the linearly independent columns and row are 2, therefore the rank is 2. And the system as solution. And our solution are, so think once again about them as x and y. So this is the x and this is the y. So the x is going to be equal to -3 over 2, and our y is equal to -3 over 2. So you see, this is actually way easier to do compared to this. Well, it's not actually way easier because this one was pretty simple as well. But you know, if you think about, you know, R3, R4, R5, R6, R7, R110, I don't know, dimension with many variables, a system of linear equation is actually really easier to solve by using the, you know, the Gauss reduction. So this is our solution. Therefore, you know, x is equal to y. Shall we verify it? You know, what in linear algebra is actually, well, it's not the case because, you know, this is a very simple, oversimplified example. But in linear algebra, sometimes, well, most of the times, it may happen that you make, you know, a silly mistake for whatever reason, because, you know, even though numbers are pretty simple, you may, I don't know, have a minus instead of a plus and so on, or just multiply by the wrong value. I don't know, it may happen. So just, and this is just a suggestion, but it saved me in one of my exams. Just take a little bit of time to verify that what you have found is actually correct. So, well, this is actually pretty straightforward, but we're gonna verify anyway, just to be consistent with what I just said. Very fun. I'm just gonna verify it. So, well, let's just plug in the values in our system of equation. 3, 2 minus 3 times negative 3 over 2 equals 3. So I basically plug in the value in the very first equation of our system of linear equation. And I just left it as it was, so equal to 3. Let's see. So basically get negative 3 over 2 plus 9 over 2 equal to 3. Then we get 2 negative 3 plus 9 equal 3. And so we get 6 over 2 equal to 3. Or I can simplify it, get 3, 1. So therefore we have 3 equal 3. And yes, it's verified. Verified. And a smile. Okay, so it's totally verified, and therefore our solution is fine, and our true solution is fine. So yeah, as I said again, this is an oversimplified example, but it kind of gives you a sort of example of how things can be useful in higher dimension, and how things can be done. It doesn't really make sense to start with I don't know, an R5 or an R4 dimension with many variables and take a lot of time to compute it, because this is doing it in R2 in non in the Cartesian plane is exactly the same, is really exactly the same. So okay, I hope it helps as always. Bye.